Problem 2 from 2004 is an example of a problem where we don't really have a whole lot of numbers. They want the answer in constants. Now, this is a thing that typically I don't get too freaked out with, but students tend to freak because on most of my tests we did everything with numbers. So we're practicing a little bit with a problem where we are just dealing in fundamental constants. So on this problem we have a mass, it's attached to a wheel acting as a pulley, the mass is going to be allowed to fall, and we have some distances and some times. In part A, it says calculate the linear acceleration A of the following block in terms of the given quantities. They gave us the distance that it fell, the mass, the time, and the radius of the wheel. We don't know the mass of the wheel, however, we're going to calculate the rotational inertia here in a little bit. So we're going to start off with just kinematic equation. I have a time and I have a distance. I should be able to find a linear acceleration from that. So delta y is equal to v naught yt plus 1/2 ayt squared. Start the mass off with initial velocity 0. We're going to have the delta y is d, that's the distance traveled, 1/2 a and t squared. Now check your work. Did they give you d and did they give you t? Are those the fundamental constants? In this case, the answer is yes. So we can solve for the acceleration by just having d is equal to 1/2 at squared. We get the linear acceleration is 2d over t squared. That was worth 2 points on this problem. Remember, all these problems are out of 15. Now the next one, it's asking you the time is measured and the d is measured. What quantities should be graphed in order to best determine the acceleration of the block? Well, if we graph them, we can do it a couple of different ways. What they're looking for is the slope, okay, the slope. So right here, the acceleration would be equal to rise over run. So if I put d on the y-axis and t squared on the x-axis, we're going to get a linear relationship. Now there is a factor of 2 out in front of there, but what they're asking you for is how do we get the slope from the graph? They want a linear relationship, easily find the slope, and here that would be graphing the d, the distance, along the y-axis, t squared along the x-axis. Now you need to recognize that that means that the acceleration is going to be equal to 2 times the slope, because there's a factor of 2 out in front, and we have d over t squared. So that's how we're going to solve for that guy, all right? Going on to the next one. So they ask you to graph the use the graph, find the magnitude of the acceleration. You can do that, pretty straightforward. Calculate the rotational inertia of the pulley in terms of little m, r, a, and fundamental constants. Going to move on to the other whiteboard. Okay? On the other whiteboard, remember how I said over and over again when we were studying rotations, they love this derivation that makes the connection between rotational inertia, angular acceleration, and r times f. So what they're looking for is I alpha is equal to rf sine theta. So here's what I'm starting out with. I alpha is equal to rf sine theta. The f in this case is going to be the tension. The tension meets the radius at 90 degrees, so the sine of 90 is going to be 1. So I have I alpha is equal to t times r, the tension. We don't know what the tension is, however, so I'm going to come back to that. We also recognize that the angular acceleration is going to be equal to the linear acceleration divided by r. So I can find the linear acceleration and therefore find the rotational inertia. We look at our free body diagram for the hanging mass. We have mg acting down, tension acting up, and we know this mass is going to go down. So the net force on this mass that's falling is negative ma, that linear acceleration. Tension acting up, minus mg. We solve for the tension right here. So the tension is now given in terms of mg minus ma. Those are all fundamental constants in the problem. So I'm going to take this tension and I'm going to plug it in up here, reminding myself that I'm going to have the rotational inertia times alpha. Alpha is equal to a over r. So I times alpha, a over r, is equal to mg minus ma, that's the tension right here, and then we have the r right there, the radius of the pulley. Move the r over to the other side, that now becomes r squared, the difference in mg minus ma all over a. So this is how we find the rotational inertia. I did that really fast, so let me just review. The relationship that you're looking for is I alpha is equal to rf sine theta. In this case, the r is going to be the radius of the pulley, f is going to be the tension, they meet at 90 degrees. Remember, 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 they love this correlation. They're going to show it to you over and over again. That's how we figure out our rotational inertia. And then lastly, they're just asking for what can account for the difference between your theoretical and experimental value. A couple ways that you can go about this. The book likes the answer, or the AP people like the answer of the string. As you wrap the string around, it's going to increase the radius. So the radius is going to decrease as this thing unwinds. That could be a source of error. And then you could also have friction between the pulley and the string. That could be another source of error. Okay, so not too much in this problem, but that relationship of I alpha and RF sine theta is going to come up over and over again.